Limit theorems. First, we have the limit of a constant is the constant itself. So let's say we are asked to get the limit of 4 as x approaches 2. 4 is a constant, so the limit of this is 4. Let's say the limit of 10 as x approaches negative 7. The answer here is 10. The limit of 2.15 as x approaches 5 is 2.15. The limit of x as x approaches c is equal to c. So as you can see, this is just straight substitution to our variable x. So if we are asked to get the limit of x as x approaches 2, that is equal to 2. This would be negative 7, and this would be 5. Another would be constant multiple theorem. Let's say we have the limit of k times f of x as x approaches c can also be expressed as k times the limit of f of x as x approaches c. For example, we have the limit of 5x as x approaches 2. So we can write this as 5 times the limit of x as x approaches 2. If we continue to evaluate this, we can have, based from our previous theorem, we can say that the limit of x as x approaches 2 is 2. So we can have 5 times 2. Therefore, this is equal to 10. Another example, the limit of 3x as x approaches negative 4. We can write this as 3 times the limit of x as x approaches negative 4. Continue evaluating this, we have 3 times negative 4, and we have the limit of 3x as x approaches negative 4 is equal to negative 12. The next is addition theorem. If we have the limit of f of x plus or minus g of x as x approaches c, we can write this as the limit of f of x as x approaches c plus or minus the limit of g of x as x approaches c. For example, we have the limit of x plus 2 as x approaches 2. So this can be written as the limit of x as x approaches 2 plus the limit of 2 as x approaches 2. To evaluate, we can have the limit of x as x approaches 2 is 2, and the limit of 2 is a constant, and therefore that is also 2. So we have 2 plus 2 is equal to 4. Another example, we have the limit of 2x minus 1 as x approaches 3. So for this term, we have the constant multiple theorem, so this can be written as 2 times the limit of x as x approaches 3 minus the limit of 1 as x approaches 3. So we can have 2 times the limit of x, and this would be 3 minus the limit of a constant is 1. So we have 2 times 3 minus 1, so we have 5. For the multiplication theorem, if we have the limit of the product of f of x and g of x as x approaches c, this can be written as the limit of f of x as x approaches c times the limit of g of x as x approaches c. For example, we have the limit of x plus 2 times x minus 3 as x approaches 2. So we can write this as the limit of x plus 2 as x approaches 2 and the limit of x minus 3 as x approaches 2. Applying other theorems, we can have this as the limit of x as x approaches 2 plus the limit of 2 as x approaches 2. Same with this factor, we have the limit of x as x approaches 2 minus the limit of 3 as x approaches 2. To evaluate, we can have this as 2 plus the limit of 2 is itself times, this would be 2 minus 3. Simplifying, we have 4 times negative 1, and we have negative 4. Another example, let's say we have the limit of the product of x and x plus 1 as x approaches negative 1. So we can write this as the limit of x as x approaches negative 1 times the limit of x plus 1 as x approaches negative 1. This factor can be written as the limit of x as x approaches negative 1 plus the limit of 1 as x approaches negative 1. To evaluate, this would be negative 1. Same here as negative 1, and the limit of 1 is 1. Simplifying, negative 1 plus 1 is 0, times negative 1 would give us 0. For the division theorem, we have the limit of f of x over g of x as x approaches c. So we can have this as the limit of f of x as x approaches c over the limit of g of x as x approaches c. For example, we have the limit of 2 over x as x approaches 2. So we can have this as the limit of 2 as x approaches 2 over the limit of x as x approaches 2. To evaluate, we can have this as 2, because this is the limit of a constant, over the limit of x as x approaches 2 is 2. To simplify, we have this as 1. Another example, the limit of 2x over 3 as x approaches negative 6. So this can be written as 2 times the limit of x as x approaches negative 6 over the limit of 3 as x approaches negative 6. To evaluate, we have the limit of x as x approaches negative 6 is negative 6. The limit of 3, which is a constant, is 3. Simplifying, 2 times negative 6 is negative 12 over 3 is negative 4. For the power theorem, example, let's say we have the limit of x squared as x approaches 2. So we can write this as the squared quantity of the limit of x as x approaches 2. So we have the limit of x as x approaches 2 is 2. And then squaring it, this would be 4. Another example, the limit of 2x raised to 4 as x approaches 3. The constant multiple theorem, this would be 2 times, and then power theorem, fourth power of the limit of x as x approaches 3. To evaluate, this would be the limit of x as x approaches 3 is 3 raised to 4, that is 81, times 2 is 162. For radical theorem, let's say we have the limit of the square root of x as x approaches 4. Following this theorem, we can have the square root of the limit of x as x approaches 4. To evaluate, the limit of x as x approaches 4 is 4. Taking the square root of it is 2. Let's say we have 4 times the cube root of x as x approaches 8. We have 4 times the limit of the cube root of x as x approaches 8. Evaluating this, x would be 8, and getting the cube root of 8, that would be 2, times 4, and that would be 8. This video shows examples of limits of functions in indeterminate form using factoring and rationalizing. For example 1, let's say we have the limit of x squared plus 2x plus 1 over x plus 1 as x approaches negative 1. If we try to substitute negative 1 to the given function, we would be having the square of negative 1 plus 2 times negative 1 plus 1 over negative 1 plus 1. So this is in indeterminate form because upon substitution, we have 0 over 0. Therefore, we need to do another work to identify the limit of this function, and that would be factoring. The numerator can be written as x plus 1 times x plus 1, for these are the factors of the numerator. We can cancel x plus 1 from the numerator and the denominator, leaving us the limit of x plus 1 as x approaches negative 1. we can now substitute -1 to x, and that would be -1 plus 1. So the limit for example 1 is 0. For example 2, the given is x squared plus 5x minus 14 all over x squared minus 4 as x approaches 2. Let us show that this is really in indeterminate form by substituting 2 to our x. So we would be having 4 plus 5 times 2 is 10 minus 14, and that would be 0 over 0. Getting the factors of the numerator would be x plus 7 and x minus 2. Also, the denominator would be the sum and difference of two binomials, and that would be x plus 2 times x minus 2. We can cancel x minus 2, leaving us the limit of x plus 7 over x plus 2 as x approaches 2. By substitution, we can have 2 plus 7 over 2 plus 2. So the limit of this function is 9 over 4. For example 3, the given is x squared minus 4x minus 5 all over x squared plus 10x plus 9 as x approaches -1. Let us show again that this is really in indeterminate form by substituting -1 to the x in our function. So we have -1 squared is 1, -4 times -1 is +4, minus 5, over -1 squared is 1, 10 times -1 is -10, plus 9. So we have 0 over 0. Let us now do factoring for the given function. So to factor the numerator, we have x minus 5 times x plus 1. And for the denominator, we have x plus 9 times x plus 1. We can now cancel x plus 1, giving us the limit of x minus 5 over x plus 9 as x approaches -1. So we can now substitute -1 to our x here. So we have -1 minus 5 all over -1 plus 9. So -1 minus 5 is -6. -1 plus 9 is 8. Simplifying, we can have -3 over 4. For example 4, let's have the limit of x minus 16 over the square root of x minus 4 as x approaches 16. To show that this is in indeterminate form, let us substitute 16 to the variable x. So we have 0 over 0. To get the limit of this function as x approaches 16, we're going to do rationalization. Therefore, we need to multiply this function to the conjugate of the denominator. So in this case, we have the square root of x minus 4 as the denominator, so we need to multiply it by square root of x plus 4 over the square root of x plus 4. So as you can see, we just changed the sign of the denominator here. So this would be minus, and for this factor, you just have to do it as addition. Since the denominator is the sum and difference of two binomials, we can use special products to simplify. So we can have the square of the square root of x minus the square of 4. To simplify the denominator, we would be having x minus 16. We can cancel x minus 16. giving us the limit of the square root of x plus 4 as x approaches 16. By substitution, we can have the square root of 16 plus 4. So we have 4 plus 4, and that would be 8. For example 5, the limit of the square root of a plus 4 minus 2 over a as a approaches 0. To check if this is really an indeterminate form as a approaches 0, let us substitute 0 to our variable a. So we have 0 plus 4 minus 2. So we have square root of 4, and that would be 2 minus 2 over 0. So we have 0 over 0. Let us multiply the square root of a plus 4 plus 2 over the square root of a plus 4 plus 2 to our function to rationalize. So same step as our example 4. As you can see here in the numerator, we can perform special products. Since our numerator shows the sum and difference of two binomials. Therefore, we can have the square of the square root of a plus 4 minus 2 squared all over a times the square root of a plus 4 plus 2. Simplifying the numerator, we can have a plus 4 minus 2 squared is 4. We can still simplify the numerator. So 4 minus 4 is 0 plus a, and that would be a. We can cancel a, giving us 1 over the square root of a plus 4 plus 2. We can now substitute 0 to our variable a. So we have 1 over the square root of 0 plus 4 plus 2. This would be square root of 4, and that would be 2 plus 2, so that would be 4 for the denominator. Therefore, the limit for example 5 is 1 over 4. For example 6, we have the limit of 3 minus the square root of x squared plus 9 all over x squared as x approaches 0, showing that this would be 0 over 0. We have to substitute 0 to our variable x. To evaluate the limit, we need to multiply this function to 3 plus the square root of x squared plus 9 over 3 plus the square root of x squared plus 9. Again, the numerator shows sum and difference of two binomials. So we can solve this by doing 3 squared minus the square of the square root of x squared plus 9 over x squared times 3 plus the square root of x squared plus 9. So simplifying the numerator, we can have 9 minus x squared plus 9 because the radical sign would be cancelled because we are squaring this term. So simplifying our numerator, we can have 9 minus x squared minus 9, distributing the negative 1 here. So therefore, we have negative x squared over the denominator here. And as you can see, we can cancel x squared, leaving us the limit of negative 1 all over 3 plus the square root of x squared plus 9. We can now substitute 0 to the variable x. So to simplify, this would be 0 squared plus 9, and the square root of 9 is 3. So we can have negative 1 over 3 plus 3, and that would be negative 1 over 6. For our last example, let's say we have the limit of the square root of 1 plus x minus the square root of 1 minus x over x. as x approaches 0. Showing that this would be 0 over 0, we have to substitute 0 to the variable x. The square root of 1 minus square root of 1 is 0 over 0. To get the limit of this function, we need to multiply this by the conjugate of the numerator. So we have the square root of 1 plus x plus the square root of 1 minus x, all over the square root of 1 plus x plus the square root of 1 minus x. The numerator shows the sum and difference of two binomials. Therefore, we can simplify the numerator by doing special products, and that would be the square of the square root of 1 plus x minus the square of the square root of 1 minus x all over the denominator. Squaring this would give you 1 plus x minus 1 minus x. Distributing negative 1 to 1 minus x, we can have negative 1 plus x. 1 plus x minus 1 plus x would give you 2x. And then we can cancel x, giving us 2 over the square root of 1 plus x plus the square root of 1 minus x. Substituting 0 to the given function, we can have the square root of 1 plus the square root of 1, and that would be 2 for the denominator. So simplifying, you have 2 over 2, and that is 1. In this video, we're going to show a strategy on how to solve infinite limits. So how can we say that the limit of f of x as x approaches c is either positive or negative infinity? For positive infinity in reference to the given graph, let's say that this vertical asymptote is c. And for this graph, the vertical asymptote here is also c. Now, for this graph, we can see that as the value of x gets closer and closer to c, f of x increases without bound. And for this graph, as the value of x gets closer and closer to c, f of x decreases without bound. So let us try to answer some examples. Let's say we have the limit of 1 over x minus 3 as x approaches 3 from the left. So the first thing to do is to find f of 3, or to plug in 3 to the given equation. So we have 1 over 3 minus 3. So f of 3 is equal to 1 over 0. So we can say that we have a vertical asymptote at x is equal to 3. So whenever we have the answer that is a finite number over 0, then probably we would be having a vertical asymptote at that number. Because if we have 0 over 0, we're going to use a different strategy. So how do we answer this problem? It is stated here that as x approaches 3. So if we refer to the number line, let's say we have 2, this is 3, and 4. And we are asked to get 3 from the left because of the superscript here. So if it's from the left, let us try to substitute values that would be from the left of 3. So let's say we're doing 2.9999. So doing that, we have 1 over 2.999 minus 3. And then Let us consider the sign of the output here. So for the numerator, we have positive over 2.999 minus 3, we have a negative number. And then performing the operation, we have positive divided by negative, we have negative infinity. So for this example, the answer is negative infinity. Let us check using its graph. So we can see here that we have the vertical asymptote at 3. And as x get closer to 3 from the left, f of x decreases without bound. Therefore, this is negative infinity. For example 2, let's say we have the limit of x minus 5 over x minus 6 as x approaches 6 from the right. So let us first try to get f of 6. So we have 6 minus 5 over 6 minus 6. So we have f of 6 is equal to 1 over 0. So therefore, we're going to do the strategy for infinite limits. So let us try to substitute values from the right of 6. So in reference to the given function, let's say we have 6.001 minus 5 over 6.001 minus 6. Analyzing the signs would be, the numerator would give us a positive answer over a positive answer. So positive divided by positive, that would be positive, and that is infinity for our example 2. Let us check using its graph. So we have a vertical asymptote at x equal to 6. So from the right of 6, tracing its graph, as x get closer and closer to 6, f of x increases without bound, or to positive infinity. For example 3, let us try to get the limit of 1 over x as x approaches 0. So doing f of 0, okay, we have 1 over 0. So let us get the limit from the right of 0 and from the left of 0. So in reference to our number line, let's say this is 0, this is negative 1 and 1. So if you would like to try values that would be from the left, from the right of 0, let's say here from the right of 0, let's try 0.001. And from the left, let's say we have negative 0.001. So here, let's say we have 1 over 0 from the right, let's have 0.001. For the signs, numerator is positive over positive. So positive divided by positive is positive, and therefore we have positive infinity. For this case, we have 1 over left of 0, let us try negative 0.001. And that would be positive over negative. And we have negative, and this is infinity. Since the left-hand limit is not equal to the right-hand limit, we can say that the limit for 1 over x as x approaches 0 does not exist. To check its graph, this would be the vertical asymptote at 0. And as we move closer and closer to 0, from the right, we have positive infinity. And from the left, we have negative infinity. So we have does not exist. For example 4, let's have 4 over x plus 4 as x approaches negative 4. So let's try to do f of negative 4. So that would be 4 over negative 4 plus 4. So f of negative 4 is equal to 4 over 0. So again, we have a finite number over 0. So we're going to do the strategy for infinite limits. So let's use the limit of 4 over x plus 4 as x approaches negative 4 from the right, and this would be from the left. Let us consider again our number line. Let's say we have negative 4, and then this is negative 5, and this is negative 3. So from the right of negative 4, we have negative 3.999. And from the left of negative 4, we have negative 4.001. Let's try those numbers. So from the right, we have 4 over negative 3.999 plus 4. And from the left, we have 4 over negative 4.001 plus 4. So let us analyze the signs. For the numerator, we have positive over negative 3.999 plus 4 would give us a positive answer. So positive divide positive is positive. For this case, for the numerator, we have positive over negative 4.001 plus 4 is negative, and therefore we have negative infinity. From the right is positive infinity, and from the left is negative infinity, therefore we have D and E, or does not exist. Let us check using its graph. So vertical asymptote at x is equal to negative 4. So as we move closer to negative 4 from the right, we have positive infinity, and the limit as we move closer from the left of negative 4, we have negative infinity, or f of x decreases without bound. So therefore, this would be D and E. For example 5, let us try to have f of 2. So we have 3 over negative and then 2 minus 2 and then square. So doing this, f of 2 would give us 3 over negative 0. So again, we have a finite number over 0. So we're going to do the strategy for infinite limits. So let us have the right-hand limit and the left-hand limit. Okay, so let us try to substitute values from the right of 2. So let us have 2.001 minus 2 whole square. So for the signs, the numerator would be positive over 2.001 minus 2 would give us a positive answer. Squared would be positive times negative here would be negative. So this would be negative infinity. For the limit from the left of 2, let us try 1.999 minus 2 and squared. So the numerator would be positive over 1.999 minus 2 is a negative number, squared would be positive, times negative 1 would be negative. So this would be negative infinity. Therefore, the answer here is negative infinity, since the right-hand limit is equal to the left-hand limit. Let us use its graph to check. So we can see here we have the vertical asymptote at x is equal to 2. So from the left of 2, f of x decreases without bound. Same with from the right of 2. So therefore, this is negative infinity. For example 6, let us try to substitute 10 over 3 to our given function. So 7 times 10 over 3 over 10 minus 3
times 10 over 3 raised to 4. So f of 10 over 3, this would be cancelled. So therefore, we would be having 10 minus 10 raised to 4. And that would still be 0. So we have 70 over 3 over 0. So again, this is a finite number over 0. Then we would be using infinite limit strategy. So let us analyze again our number line. 10 over 3 is around 3.33. So let's say we have 2 and 3 and then 4. So 3.33 is somewhere here. So this is 10 over 3 or 3.33. So if we assign values from the left of 3.33, and that is a positive number, and then substitute it to our x here, for the numerator, 7 times a positive number, we have positive over, for the denominator, we have a positive answer because of our even exponent here. Therefore, positive divided by positive would be positive, and this is infinity. Let us check using its graph. So as you can see here, we have a vertical asymptote at 3.33 or 10 over 3. And as x get closer and closer to 3.33, from the left, okay, f of x increases without bound. So this is positive infinity. In this video, we're going to cover limits at infinity of polynomial functions and some rational functions. Before that, let us establish the idea that the limit of a over x raised to r as x approaches infinity is equal to 0, where a is any real number and r is a positive rational number. Let me give you examples using graphs. Let's say we have f of x is equal to 1 over x. So 1 is a real number, and then the exponent of x here is the rational number. So this is the graph of 1 over x. So as you can see on the behavior of our f of x, as x increases its value without bound, the y value approaches 0. On the other hand, as x decreases its value without bound, y approaches 0. Another example, let's say we have f of x is equal to negative 7 over x squared. In reference to this graph, as the value of x increases without bound, the y value gets closer to 0. Same here on this side, as x decreases without bound, y value approaches 0. This is the graph for 3 over x raised to 4. So same thing, as x increases without bound, the y value approaches 0. Same here, as x decreases without bound, the y value gets closer to 0. So for example 1, let us try to get the limits at infinity of polynomial functions. So how do we identify the limits at infinity? So let us consider the term with the highest degree. So in this case, negative 3 x cubed would be the term with the highest degree. So if we try to substitute infinity to x, therefore we are dealing with a very large number times a negative. So therefore, this would be negative infinity. Here, we are approaching negative infinity. So if we try to substitute negative infinity to x, that would be negative infinity times negative infinity times negative infinity. It would give you negative infinity. And then if you multiply it to negative 3, it would be positive infinity. Another strategy would be by using factoring. So if we're going to do the limit as x approaches infinity, and we have the function, if we factor out x cubed, we would be having here negative 3 plus 2 over x squared. And then applying the theorems, we have limit of x cubed as x approaches infinity times the limit of negative 3 plus 2 over x squared as x approaches infinity. So what we have here would be the limit of x cubed as x approaches infinity times, remember that the limit of a over x raised to r as x approaches infinity is equal to 0. Here, 2 over x squared would have the limit of 0 as x approaches infinity. Therefore, we would be having the limit of negative 3 as x approaches infinity. So if we try to substitute infinity to our x here, we would be having a very large number times negative 3. The limit of a constant is itself. Therefore, the answer here is negative infinity. For this case, we're going to do the same factoring and application of the limit theorems. So what we have here would be the limit of x cubed as x approaches negative infinity. For this part, the limit would be 0. So what we have would be the limit of x cubed as x approaches negative infinity times the limit of negative 3 as x approaches negative infinity. So if we try to substitute negative infinity to x cubed, then we would be having a very large number, which is a negative number. So negative infinity times negative infinity times negative infinity. And then, if we multiply it to a negative constant, then it would be positive infinity. Let us verify using its graph. So this is the graph of negative 3x cubed plus 2x. So as the value of x increases without bound, in this case, let us trace the graph. As the value of x increases without bound, the value of y decreases without bound. So the answer here is negative infinity. So for this one, as x decreases without bound, let's look at the graph, the y value increases without bound. So this is positive infinity. Okay, so let us try to answer some additional examples. Let's say we have the limit of x cubed plus 2x raised to 4 minus 3x as x approaches infinity. So we're going to consider the term with the highest degree, so that would be 2x raised to 4. So applying x approaches infinity, we can have 2 and then infinity raised to 4. So we have a very large number raised to 4 would be a positive number times positive 2 would be positive infinity. Let's see, we have the limit of negative x raised to 5 plus 2x squared plus 4x raised to 3 as x approaches negative infinity. So we're going to consider negative x raised to 5. So we have negative times negative infinity raised to 5.
So we have a very large number raised to 5, a negative number here, so that would be equal to a negative number, times negative 1 here would be positive infinity. If we have the limit of 2x cubed minus x squared plus 1 as x approaches infinity, so we're going to consider this term, and we have 2 times negative infinity raised to 3. So we have a very large number raised to 3 is negative infinity times 2, so that would be a negative infinity. And finally, for this set, we have the limit of 6x cubed minus 5x squared minus x raised to 4 as x approaches infinity. So we have this as our term with the highest degree, and we have negative of infinity raised to 4. So infinity raised to 4, we would be having a very large number times a negative number, and that would be negative infinity. So how about we would like to get the limits at infinity of a given rational function. So when we say rational function, we have a polynomial over a polynomial. So we're going to use this strategy first. So the first step is for you to divide each term of this fraction by the variable x with the highest degree in the denominator. So we're going to have x squared. So we would be having x over x squared minus 2 over x squared over 2 x squared over x squared plus 5 over x squared. Of course, do not forget to write the limit notation. And then simplifying, we have the limit as x approaches infinity. So simplifying x over x squared is 1 over x minus 2 over x squared over 2x squared over x squared is 2 plus 5 over x squared. Let us recall the idea that the limit of a over x raised to r as x approaches infinity is equal to 0. So if we would like to get the limit of each term of our fraction here, negative 2 over x squared would have a limit of 0. 1 over x would have a limit of 0. Same with 5 over x squared. So what we have here would be the limit of 0 over 2 as x approaches infinity. So 0 over 2 would be 0. So we're getting the limit of 0 as x approaches infinity. And that would be 0. Let's say, for example, 4, we have the limit of 4x raised to 4 plus x plus 2 all over 2x raised to 4 minus 3 as x approaches negative infinity. So the variable x with the highest degree in the denominator is x raised to 4. So we have the limit as x approaches negative infinity. And then we're going to use x raised to 4 as a denominator of all the terms of our rational function here. So we have 4x raised to 4 over x raised to 4 plus x over x raised to 4 plus 2 over x raised to 4 over 2 x raised to 4 over x raised to 4 minus 3 over x raised to 4. And then let us simplify our function here. So we have 4x raised to 4 over x raised to 4 is 4 minus, that would be 1 over x cubed plus 2 over x raised to 4. 2x raised to 4 over x raised to 4 is 2, and then minus 3 over x raised to 4. And again,
we need to remember the concept of the limit of a over x raised to r as x approaches infinity is equal to 0. So negative 1 over x cubed would give us a limit of 0. Same with 2 over x raised to 4 and negative 3 over x raised to 4. So what's left would be 4 over 2. And 4 over 2 is 2. The limit of a constant is itself. Therefore, the answer here is 2. For this example, we have x cubed as the variable x with the highest degree in our denominator. So we have the limit as x approaches infinity. So x raised to 4 over x cubed minus x squared over x cubed plus 2 over x cubed over x cubed over x cubed plus 2 x squared over x cubed minus 8 over x cubed. Simplifying, we have x minus 1 over x plus 2 over x cubed over 1 plus 2 over x minus 8 over x cubed. Continuing, we have this would be limit is 0, same here, same as 2 over x and negative 8 over x cubed. Again, we're using the limit of a over x raised to r as x approaches infinity is equal to 0. So what we have here is the limit of x over 1 as x approaches infinity, or simply x. And then, trying to substitute infinity to x, we have infinity. Now let us consider other strategies in getting the limits at infinity of rational functions. If the given function has the degree of the numerator less than the denominator, then the limit is equal to 0. In our previous example, we have x minus 2 over 2x squared plus 5 as x approaches infinity. So here, the degree of the numerator is less than the degree of the denominator. Therefore, the limit is 0. Or you can also do the limit of x over 2x squared as x approaches infinity. Trying to simplify this would be the limit of 1 over 2x as x approaches infinity. So remember that if we have a number over the variable x and then x approaches infinity, that is equal to 0. Next, if we have the degree of the numerator is greater than the degree of denominator, the limit is either positive infinity or negative infinity. So let's say we have this function. So in the numerator, x raised to 4 would be the highest degree, and in the denominator, we have x cubed. So giving us the limit of x raised to 4 over x cubed as x approaches infinity. Simplifying, we have x raised to 4 over x cubed, that would be x. And trying to evaluate the limit of x as x approaches infinity, this would be positive infinity. Okay, if we substitute infinity to the variable x. And finally, if we have the degree of the numerator is equal to the degree of the denominator, the limit is the ratio of the coefficients of the highest degree. For example, 4x raised to 4 has the highest degree in our numerator, and we have 2x raised to 4. Therefore, we have the limit, as x approaches negative infinity, of 4x raised to 4 over 2x raised to 4. If we try to simplify, we have 4x raised to 4 over 2x raised to 4. This would be cancelled, so I have 2. The limit of a constant is itself, so we're getting the limit of 2, therefore this is 2. Or just get the value of the coefficients of the variable with the highest degree, and that would be 4 divided by 2. So we have 2.
In this video, we're going to cover continuity of a function at a number. A function is said to be continuous at a number if all these are satisfied. First, f of c exists, the limit of f of x as x approaches c exists, and the limit of f of x as x approaches c is equal to f of c. Let us have some examples. Let's say, for example, 1, we need to identify if the given function is continuous at the given value of x. So for this item, our function is 3x minus 2, and we need to identify if this function is continuous at x is equal to 2. So let us have f of 2. So doing this, we just need to substitute the given value of x to our function. So we would be doing 3 times 2 minus 2, and therefore I have 6 minus 2, and this is 4. Next, we need to get the limit of the given function, so 3x minus 2, as x approaches 2. So we have to get the limit of 3x as x approaches 2 minus the limit of 2 as x approaches 2. So by substitution, we have 3 by 2 minus 2. So we have 6 minus 2, and this is 4. Since f of c, which is 4, is equal to the limit of the function as x approaches 2, then the function is continuous at x is equal to 2. Let us try for this function, x squared plus 2x minus 4 at x is equal to 1. So let us have f of 1. So we have 1 squared plus 2 times 1 minus 4, and therefore we have 1 plus 2 minus 4. So this will be 3 minus 4, and we have negative 1. So let us get the limit of x squared plus 2x minus 4 as x approaches 1. So this would be the limit of x squared as x approaches 1 plus 2 times the limit of x as x approaches 1 minus the limit of 4 as x approaches 1. And by substitution, we have 1 squared plus 2 times 1 minus 4. So 1 plus 2 minus 4, and this would be negative 1. So f of 1 is equal to the limit of the function as x approaches 1. Therefore, the function x squared plus 2x minus 4 is continuous at x is equal to 1. So generally speaking, if you classify the given functions, these are both polynomial functions. And if you are dealing with polynomial functions, these are continuous everywhere. So whatever given value of x, we can always conclude that the function is continuous, because polynomial functions are continuous everywhere. Let us have another example. In this case, we are given a rational function. So let us try to do f of 5. So if we try to substitute this to our given function, we have 5 squared minus 6 times 5 plus 5 over 5 minus 5. So this would be 25 minus 30 plus 5 over 0. So we have 0 over 0. And therefore, f of 5 is undefined. So in this case, since f of 5 does not exist, therefore, we can say that the function is discontinuous at x is equal to 5. Since the given function is a rational function, we have to take note that rational functions are continuous at its domain, meaning to say that the function is only continuous to some values of x except for the values of x that would make our denominator 0. Let's have example 3. Let's say we have this piecewise function and we would like to identify if this function is continuous at x is equal to 3. Examining the function, we can say that the function is continuous everywhere except possibly at x is equal to 3. So let us verify. So let us have f of 3. So for f of 3, in reference to the given function, f of 3 is equal to 6. When x is equal to 3, y is 6. Let us now get the limit of the function as x approaches 3. So in reference to the given piecewise function, we're going to use x squared minus 9 over x minus 3. If we're going to do f of 3 for this function, we would be doing, for this case, that would be 3 squared minus 9 over 3 minus 3. So I have f of 3 is equal to 9 minus 9 over 0. So I have 0 over 0. So we have indeterminate in form for this given function. Therefore, we would be doing factoring. So I have x minus 3 and x plus 3 over x minus 3. So this would be cancelled. So what's left would be the limit of x plus 3 as x approaches 3. And by substitution, we would be having 3 plus 3, and therefore, the limit of this function is equal to 6. Now, we compare f of 3 and the limit of x squared minus 9 over x minus 3 as x approaches 3, or the left-hand side and the right-hand side limit of the given function. Since they are equal, then we can say that the function is continuous at x is equal to 3. For another example, we have this piecewise function, and we would like to get if the function is continuous or not at x is equal to 2. This function is continuous everywhere except possibly at 2. So let's have f of 2. So between the two functions, we're going to use x cubed minus 2x plus 1 because of the restriction of less than or equal to. So we would be having 2 cubed minus 2 times 2 plus 1. So this would be 8 minus 4 plus 1. Therefore, we have 5 for f of 2. Now let us have the limit of the function as x approaches 2. So let us first get the left-hand side of the limit, or 2 from the left. So between the two functions, we are going to use x cubed minus 2x plus 1. So this would be the limit of x cubed as x approaches 2 from the left minus 2 times the limit of x as x approaches 2 from the left plus the limit of 1 as x approaches 2 from the left. So we have 2 cubed minus 2 times 2 plus 1. So we have 8 minus 4 plus 1, and this would be 5. Now let us try to get the limit of the function as x approaches 2 from the right. So we're going to use the second function now because of this restriction, which is x is greater than 2. So we have 3x minus 2. So we can have the limit of 3x as x approaches 2 minus the limit of 2 as x approaches 2. And therefore we have 3 by 2 minus 2. So we have 6 minus 2. And therefore we have 4. Comparing the left-hand side limit to our right-hand side limit, we can say that the limit of the function as x approaches 2 does not exist because this one is not equal to 4. And therefore, since the limit does not exist, we can say that this function is discontinuous at x is equal to 2. In this video, we're going to answer some common problems on continuity on an interval. Let's say, for example, 1, we are asked to identify if the function is continuous on -5 to 5. So examining the function here, we have 3x minus 1 over x minus 4. The domain of the given function would be all real numbers except 4. So if we're going to do f of 4, and then we do direct substitution, we have 3 times 4 minus 1 over 4 minus 4. So we have 11 over 0. Because f of 4 is undefined, then we are discontinuous at x is equal to 4. In reference to the given interval, x is equal to 4 is included in the given interval. Therefore, the function is discontinuous at x is equal to 4. Another example, let us identify if the given piecewise function is continuous on the given interval. So we have x plus 1 and x over 4 plus 7. These are both polynomial functions. And polynomial functions are continuous everywhere. But since this is a piecewise function, this function may possibly be discontinuous at 8. So let us try to verify. So let us have f of 8. So we have 8 over 4 plus 7. We're going to use the second function here for f of 8. So this would be 2 plus 7. And therefore, we have 9. So let us try to identify first the limit of the function as x approaches 8 from the right. So we're going to use x plus 1 for the right-hand side limit. So we have 8 plus 1, and therefore this is 9. Let us now get the limit of the function as x approaches 8 from the left. So we're now going to use the function x over 4 plus 7. So by substitution, we have 8 over 4 plus 7, and we have 2 plus 7, and therefore we have 9. Since the right-hand side limit is equal to the left-hand side limit, then the limit of the function as x approaches 8 is equal to 9. And since f of 8 is equal to the limit of the function as x approaches 8, then we can say that the function is continuous at 8. And on the given interval 4 to 10, the function is continuous. For example 3, let us identify the intervals where the given function is continuous. So 2 minus x is a polynomial, same with x squared plus x minus 1. So we can say that the function would be continuous everywhere, except possibly at x is equal to 1. So let us try to verify. Let us first get f of 1, and we're going to use the function x squared plus x minus 1. So we have 1 plus 1 minus 1, and we have 1 for f of 1. Let us now get the limit of the function as x approaches 1. So let's try to get the limit of the function as x approaches 1 from the right. So we're going to use x squared plus x minus 1. So by direct substitution, we have 1 squared plus 1 minus 1, and therefore this will be 2 minus 1, and we have 1. For the left-hand side limit, we're now going to use the function 2 minus x. So we have 2 minus 1, and therefore we have 1. Since the left-hand side limit is equal to the right-hand side limit of the given piecewise function as x approaches 1, then the limit is equal to 1. Since f of 1 is equal to the limit of the function as x approaches 1, then the function is continuous at x is equal to 1. Therefore, to answer the question on the intervals, we can say that the function is continuous on the interval negative infinity to infinity. Another example, we would like to identify if the given function is continuous on the given intervals. So we have to answer 4 items. So before that, let us take a look at our function. So as you can see, we're given a piecewise function, and 2x over x minus 4 is a rational function. Same with 5x over x minus 3. So let's first try to get f of 4. So we're going to use the function 5x over x minus 3. So we have, by direct substitution, we have 5 times 4 over 4 minus 3. So this would be 20 over 1, or simply 20. Let's now get the limit at x is equal to 4. So first, let us get the left-hand side limit of the function. So that would be 4 from the left. So we're going to use the function 5x over x minus 3. So by direct substitution, this would be the same as f of c, and therefore we have 20. Let us now get the limit of the function as x approaches 4 from the right. So we're going to use 2x over x minus 4. And then upon looking at our function, if we try to substitute 4 to our equation, we would be having undefined. Or to be exact, that would be 8 over 0. And if that is the case, we are dealing with infinite limits. So what we're going to do now is to use values from the right of 4. So let us write 4.001 times 2, 4.001 minus 4. So for the numerator, our expected answer is positive, and for the denominator, same is positive. Therefore, the limit of the function as x approaches 4 from the right is positive infinity. And since the left-hand side limit is not equal to the right-hand side limit, then the limit of the function as x approaches 4 does not exist. And therefore, we are discontinuous at x is equal to 4. Now, going back to the given function, the second function, 5x over x minus 3, is discontinuous at x is equal to 3. Because when we substitute 3 to our denominator, for example, let us try to have f of 3 for 5x over x minus 3. So we have 3 minus 3, and therefore f of 3 would be 15 over 0, which would give us undefined. And because of this, we can say that we are also discontinuous at x is equal to 3. Now, going back to the question, let us try to answer. From our solution, we are discontinuous at x is equal to 3 and x is equal to 4. So if those numbers are included in the given interval, then the function is discontinuous. So let us try to answer number 1, 2 to 5. This is discontinuous. I'm going to write D for discontinuous and C for continuous. For number 2, negative infinity to 3. This is continuous. Though we are discontinuous at 3, but we're just referring to all the numbers between negative infinity to 3. So we are not including 3 in the given interval. For 3 to 4, this is also continuous. Though we are discontinuous at x is equal to 3 and x is equal to 4, but we are excluding those numbers in the given interval. Therefore, the function is continuous on this interval. And for 5 to infinity, this is also continuous because x is equal to 3 and x is equal to 4 are not included in the given interval. In this video, we're going to cover continuity through graphs. So we're just going to examine the given graph and then identify if the given function is continuous. Let's say we are given values of x, and we would like to identify if the function is continuous. The basic idea of identifying if the function is continuous, in this case at the given value of x, is if we can draw the graph without lifting our pen, or by looking out at holes, gaps, breaks, or vertical asymptotes at the given value of x. So let's say we would like to identify if the function is continuous at x is equal to negative 4. So this is x is equal to negative 4. So if you look at the graph, we do not see holes, gaps, or breaks. Therefore, this would be continuous. So I will just write C for continuous and D for discontinuous. Let's see for x is equal to 2. So this is x is equal to 2. As we can see, we have a gap at x is equal to 2. So this is discontinuous. So let's say for x is equal to 7. We do not see any discontinuity. Therefore, this is continuous. For x is equal to 5, so we can see there is a gap at x is equal to 5. So this is discontinuous. X is equal to negative 2 is here. We can see that there is a vertical asymptote since the right-hand side is moving to positive infinity and the left-hand side is moving to negative infinity. Therefore, at x is equal to negative 2, we are discontinuous. And for x is equal to negative 5, we can see a hole at x is equal to negative 5. So this is also discontinuous. Now let us identify if the given function is continuous on the given interval. So this time, we're not just looking at a specific value of x, but we are looking at a span of values of x. So we have to be mindful of the given interval, if it's open or closed interval. So let's start with negative 4 to negative 3. So for this symbol, this is an open interval, meaning we are including all the values between negative 4 and negative 3, excluding negative 4 and negative 3. So in reference to our given graph, this would be x is equal to negative 4, and this would be x is equal to negative 3. If we try to trace the graph from negative 4 to negative 3, and we do not see any holes, gaps, breaks, or asymptotes, therefore, this is continuous. Let's say for the interval 2 to 4. So, in this interval, 2 is included. So in reference to our given graph, this would be 2 to 4. So from 2 to 4, there is a hole at 2. Therefore, the function is discontinuous on this interval. Let's say for 0 to 2. So let us refer to the given graph. This is 0, this is shaded, and then this would be up to 2. And this is also shaded. We do not see any holes, gaps, or break on this interval. Therefore, this is continuous. For this case, what we would like to see is the interval from 0 to 2. So even if we are discontinuous at 0, our concern is the graph from 0 to 2, because this would be the values from the left of 0. Next, we have 5 to infinity. So 5 to infinity is here, not including 5 to infinity. Therefore, this is continuous. Negative 6 to negative 2. Negative 6 to negative 2, as we can see, we are including a hole inside the interval. So therefore, this is discontinuous. For negative 2 to 0, this would be negative 2 to 0. And in the given interval, we are including negative 2. And since we have a vertical asymptote at negative 2, therefore, this would be discontinuous. continuous. And for negative infinity to negative 5, we are not including the negative 5 wherein we have a whole. Therefore, this is continuous. In this video, we're going to cover types of discontinuities. And these are removable or whole discontinuity, which would give us that f of c is not equal to the limit of the function as x approaches c. So in this case, the limit exists. Jump discontinuity, we have the limit of the function as x approaches c from the left is not equal to the limit of the function as x approaches c from the right. In this case, the limit does not exist. For infinite discontinuity, either side of the limit of the function as x approaches c is infinite. Let us have some examples. So first, let us identify f of 4. By direct substitution, we can have 0 over 0. Therefore, f of 4 is undefined. Since we have 0 over 0, to get the limit, we can do factoring. So this would be cancelled, giving us the limit of x plus 4 as x approaches 4. By direct substitution, we can have 4 plus 4, and we have 8. From this case, the limit exists, which is 8, and it is not equal to our f of c. Therefore, the type of discontinuity is removable or whole. Another example, let's say we have x minus 2 over x minus 5, and we would like to get the discontinuity at x is equal to 5. So getting f of 5, we have 3 over 0. So f of 5 is undefined. In this case, we have a number over 0, or a finite number over 0. So we're going to do the strategy for infinite limits. So to get the limit from the right side of our function, we would be doing 5.001 minus 2 over 5.001 minus 5. So expected answer for the numerator is positive over positive. So this is positive. Therefore, we have positive infinity. So we're going to use 4.999 minus 2 over 4.999 minus 5. So for the signs, we have positive over negative. So this would be negative infinity. So the limit at x is equal to 5 does not exist. But to identify the type of discontinuity, since we have infinite limits, then this is infinite discontinuity. For another example, let us identify the type of discontinuity at x is equal to negative 1. So solving for f of negative 1 for this piecewise function, we're going to use the first function, which is x minus 3. So by direct substitution, we have negative 1 minus 3. And therefore, this is negative 4. Let us now identify the limit of the function as x approaches negative 1. For the right-hand side limit, we're going to use x squared minus 3x minus 1. And for the left-hand side, we're going to use x minus 3. So by direct substitution, this would be negative 1 squared minus 3 by negative 1 minus 1. So this is 1 plus 3 minus 1. So we have 3. And for the left-hand side, this would be -1 minus 3, and that is -4. Therefore, the limit at x is equal to -1 does not exist. And to identify the type of discontinuity, checking our limits, we have real numbers. And therefore, we have a jump discontinuity at x is equal to -1. This graph shows some of the examples of the types of discontinuities. So let's say this is C, and here. Now, for the first graph, this shows a removable discontinuity. As we can see, the limit exists and is not equal to f of c. This would be a jump discontinuity. As we can see, there is a gap at x is equal to c, or the limit from the left-hand side is not equal to the right-hand side limit. And for the infinite discontinuity, we can see an asymptote. So let us try to answer this exercise. Let us identify the type of discontinuity at the given value of x. So at x is equal to -3, here the limit exists and we do not see any defined values. Therefore, this is removable. At x is equal to -2, there is a gap, so we have jump. At x is equal to 2, there is a vertical asymptote, so we have an infinite discontinuity. At x is equal to 3, the limit exists, and f of 3 is equal to 1. So the limit is not equal to f of c. So this is removable or whole. And at x is equal to 0, there is a gap. Therefore, we have a jump discontinuity.